Assalamualaikum and good day everyone. Okay, in previous lecture you learned about min-term, max-term, canonical SOP and canonical POS, and you also learned how to write it in the corresponding function where your min-term will be in small capital of M, right, and your max-term is in the capital of M. Okay, and you know min-term is using sum of products and maximum using product of sum. Okay, and here the function will be one, the one that we're going to be interested at, and here the function will be 0. Okay, and then for the min-term, the 0, the true value, for example the A, if it's A is 1, then you will have like this. Okay, and if your B is 0, means it is complemented, so it will be written like this. Okay, and because it's sum of product, so it is dot, and we will have like multiple of addition. Okay, this is for the case of two variable. Okay, for the case of POS here, you will have like in terms of product of sum, you will have summation, and the function here is 0. And in contrast with this, with SOP, the one that is 0 we consider as the true value will be considered as inverse, and the one with the complemented will be considered as the one inverse will be called, the one with 0 will be considered as the true value. Okay, for example, if you have your A is 1 here, then A1 and your B, for example, is 0, will result in function to be 0. Okay, so we take the one with 0, and then you have A1, so A will be written like this, and your B will be written like this. Okay, and because it's product of sum, so we have a lot of products. Okay, product of sum. Okay, now without further ado, we go to the next part. Of the lecture, okay, of the week 6. Okay, week 6 we will study about logic simplification, using K-map. Okay, K-maps, the full name is Carnot map. Okay, Carnot map, and we go to get transformation, and we will go to another one, the last one of the week 6, which is De Morgan equivalent circuit. Okay, now now we go to the truth table. We min-term and max-term notation. Okay, so how we going to write in either min-term and max-term? And okay, you guys should know that in a truth table, okay, we have a combination of variable, correct? And each of this combination of variable can be described in either min-term, which is the sum of product form, or in max-term, which is product or sum form. Okay, for example, if you have 3 input variable, okay, for example, if you have 3 input variable, for example, we take A, B, C here, and this is your input. Okay, then this is the row. Okay, the row number. Okay, if you have 3 input, then you know that you have 2 to the power of 3. You have add combination, right, of input. So we have 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and like I told you earlier, we can represent these combinations in min-term or max-term. Okay, minterm in small m and maxterm in a capital M. So I just make it a sum line here so that easy to distinguish. And here is SOP form. Here is POS form. Okay, you guys please refer to the module for more details and also from the slides. Okay, so that you have a more detailed informations. And here I'm just going to demonstrate so that for easy concept, for easy understanding for you guys, and hopefully it will you can read further from the book so that you will have more knowledge. Okay, now let's say if you have your input here, you know that it is 0, 0, 0, 0, 1 until 0, 1, 0 until you have the last value which is 1, 1, 1. Okay, this is the possible combination. Now how are we going to write the minterm here? In the minterm, you know that the true value will be represented by this, and the inverted value will be considered like this. So for example, this one is the complemented inverse value. So you have for the sum of product, you will have A because it's all 0, B and C. Okay, and this is actually your M0 small letter, and this one, how about this? And remember, it is in sum of product. Okay, so you should write in sum of product, in product form. Okay, for each of them. And 0, 0, 1, you know it is A, B, and you have finally C is 1. So this is your M1. Okay, and you have this until you can repeat until you have M7. Okay, how about maxterm? Maxterm is different. This one will be considered as 1 and this one will be considered as 0. So maxterm is product of sum. Okay, so you have here is actually A plus B plus C is equals to capital M0. How about this? It is A plus B and this plus C bar, which is your M1. Okay, capital M. Okay, so you try all of this information until you have the last one, which is the 7 maxterm. Okay, so each line in this truth table represent both minterm and maxterm. So a Boolean function, okay, a Boolean function, what is the Boolean function for f? For example, f, A, B, C, okay, can be written in terms of minterm or maxterm. Okay, as a shorthand of method of specifying the function. Okay, with referring to the page slide of 25 out of 71, okay, I give example. If we have A, B, C, okay, so we have combination like this. Okay, we have three possible combinations of variable that result in the 8 combination, right? Because it's 2 to the power of 3. Then you have your output here. Okay, they give an output. Your output is F. Okay, so for example, if you have output 0, 0, 0, and you have the rest will be 1, 1, 1, 1, 1. Okay, for example. Okay, now I try to make distinguish line here, highlight, so that you easy see it, so to able to differentiate it clearly. Okay, you guys see for the first 3 row it results in the output of 0, while the rest result in output of 1. So here we can write in minterms or maxterm. Okay, so what you guys learned before in the previous class, minterm is about the function of 1, whereas the output of 1, whereas maxterm is about the output of 0. Okay, so and minterm is SOP, maxterm is the POS. So here we're going to describe using minterm. Okay, you see this combination A bar, B, C, this one A, B, C bar, And then how about this one? A, B bar, C. And how about this? A, B, C bar. And this one is A, B, C. Okay. This is using SOP because the function SOP mean term, because the function here produce 0, A1. And how about this one? This one certainly is max term because our function, our output is 0. So we describe using max term and POS. Okay, so product of sum. So here you see this one will be considered as true. A plus B plus C. And this one A plus B plus C bar. And this one is A plus B bar plus C. Okay. So this one, when you want to put into the notation, okay, notation, so we try to describe this one first. Okay. So this one is actually 0, 1, 2, 0, 2. This one is 3 until 7. Okay, 3 until 7. So you write F, A, B, C, 3 possible inputs. Then you write back here A, B, C plus A, B bar, C bar plus A bar C plus A, B, C bar plus A, B, C. Okay. And you know that this one is actually what? Your M3. This one is M4. This one is M5. This one is M6. And this one is M7. Okay. Then you know, because is this sum or product? So it's a sum. Okay. And M, small m. And we have what? The 3th, the 4th, the 5th, the 6th, and the 7th. Okay. The next one, if we want, this one is described using max term, so it should be POS, product of sum. So we have function product of sum. So you have 3 possible combination that resulted in function 0, product of sum. So you have 3 possible combination, right? And then for this one is 0, 0, 0. So it's using the max term A plus B plus C. And how about this? A plus B plus C bar. And this one is A plus B bar plus C. Okay. So you know it's just 3 and 3 possible combination, and you know it's M0 until M2. Okay. So capital M 0, capital M1, and capital M2. And it is a product of sum. So you have your M of 0, 1, and 2. Okay. Okay. Next, we will go to the next part. Okay. Let me write for today. This is about week 6. So today is 11 April 2021. Okay. I make this lecture video on this date, but it is for the week 6. Okay. So we make some lines here, okay, so that we don't waste the space of the blank paper. So next we go to what we call as a Boolean simplification. Okay, in previous lecture you guys learned about many theorems, right? The associative, the consensus, the multiplication, and many of the theorems. So this theorem that you learned in previous lecture will be used to do the Boolean simplification. Okay. For example, if you have this question asking, for example, simplify Boolean expression below. Okay. So they asked us to simplify the Boolean expression. Now they give us A, B plus A, B plus C plus B bar, okay, B plus C. Okay, so first thing, when we see this question, we expand it first. Okay, so here you expand it, you have AB plus AB plus AC, correct? Am I correct? And then plus BB plus BC. Okay, so you also know that actually this B, this one is actually equals to only B, right? So AB and here also is equals to AB. Okay, AB plus AB. So AB plus AC plus B plus BC. Okay. Then further simplify, AB plus AC plus B, okay, 1 plus C. Okay, and here you know whatever value of C will result in this portion to be 1. Whether you have C as 1 or C as 0, you still have the total is 1. So AB plus AC plus B, because this one regardless of C it will mean 1. So you have this. Okay, actually you can further simplify it, where you factorize the B. Okay, factorize the B, then what you have 1 plus A plus AC. And the similar case for here, regardless what is your A, either 0 or 1, you will still have 1 here. So you take B plus AC. Okay, so this is the simplest one, where B equals to AC is actually where AB plus A, B plus C plus B, B plus C is equals to B plus AC. Okay. So what is the advantage of doing this Boolean simplification? One of the obvious advantage is that when you want to use a logic gates, okay, you will simplify the number of logic gate used. Okay, so instead of using many gate chips, you only use fewer gates number, fewer chip, fewer logic gate, because you have simplified the function. Okay, to be only like this possible. Okay. So we try to relate. Okay, here for example, like what is the advantage right now, right? Just now the advantage to reduce number of chip. Okay, to reduce number of logic gate use. Okay, for example, we want to reduce number of logic gates. So here obviously this one is very simple. Okay, very convenient. Reduce number of logic gate use. Okay, for example, we consider here plus, so we have OR function. Okay, then you have this as your output. Okay, then then you know you have 3 possible input, which is A, B and C. Okay, the first one is only B, direct. Okay, and the second one is A dot C, A and with C. So you have here and you have here, and you connected to N, then it goes to here. Okay, so here is actually your AC and here is actually your B. Okay, so it's easy. You only need 2 gates. Okay, you only need 2 logic gates. So what is the advantage? Further specific advantage, it is faster, compact design, and lower cost. Of course, obviously, because we use lower chip, okay, lower number of chips. And why is it faster? Like I told you guys, if we have more logic gates, we will have more delays. Okay, so this one will be faster. Okay, and I leave it to you or to all of you. Try to make this into a logic gate equivalent. Okay, it is longer and it is slower, more complicated design, and this is higher in cost. Okay, but this function will have the same function as this. Okay, will have the same output. Okay, you guys can try it home. Okay, and for example, now you have the equations from the boolean, from the logic gate, from the logic gate circuit for given logic circuits. Okay, the next part is that from the logic circuit given to you, you can derive your boolean expression. Okay, then what can you do more than that? You can simplify Boolean expression. Okay, for example, if you may receive our logic circuits which is very complex, high number of logic gates used. Okay, first step is that you derive its Boolean expression, and from there you can simplify. Okay, so you may refer to the slide 30 of 71. Okay, for this, I think it is quite straightforward. Okay, where you have your x, y, and z. Okay, and then you have some circuits in the, I just put this like this. Okay, and then we will have 3 input combination, the last stages before we go to the outputs. Okay, so from this, when you do one by one, okay, you need to do one by one, then you will come across the Boolean expression. Okay, so okay, let I just, so that I don't have time to redraw. Okay, see, so this is the logic circuits, okay, that we are trying to derive the corresponding Boolean expression. And from when we have the Boolean expression, we will simplify the Boolean expression. Okay, so here you can see for the first combination, you will get an x bar. Okay, an x bar going through here, and then you have the next one is y, so x bar y, and also z, so you have x bar y z as your first one. And the second, you have what? You have, where is the x? So you see you have your x bar, y, and z bar. So this why you have this one. Okay, x bar, y, and z bar. And the third one, you have only 2 combinations, obviously here. So you take x directly, no not gate in between, and then after that it is a z. Okay, so this is xz. So you have these combinations. Okay, then from here, okay, this is the obtainable Boolean expression. Okay, so you obtain the Boolean expression for the logic circuit, which is f equals to x bar y z plus x bar yz plus xz. Okay, so here logically is that you try to simplify this. Okay, you try to simplify this because you try to reduce the number of logic circuits involved. Okay, so for this case, for example, you have x bar yz, x bar y z bar plus xz. Okay, first you see this one is common, so you factorize x bar y, then you have z plus z bar plus xz. So from here, regardless what combination of what value of z, you still have 1, because if this is 0, this is 1. If this is 1, it will be 0 because this is inverse. So it is x bar y plus xz. Okay, so this is the simplest one. Now we try to make the simplified version logic circuits. First, you need to draw the inputs. You have x, y, and z. Okay, and see, you have your OR function. You can put it a bit far here, it's no problem. So this will perform your R. First is x bar. Okay, and end with y. Okay, and going through here. Okay, the next one is x bar, and next one is xz. So you have x and you have your z, and it's also an n. Okay, so this is your function. Okay, so you see, this is much simpler to the circuits that logic circuit that I show you at the PowerPoint, at the PDF. Okay, you guys, I will share the PDF to you. Okay, so you guys can look at it your own. Okay, okay, you guys can do the exercise available at the PowerPoint. Do at your own free time. Page slide 32 of 71 PowerPoint, or the PDF version is the same thing. Then 33 of 71. Okay, you can do yourself. Next, we go to the K-map. Okay, we go to K-map. K-map. K-map is the Carnot map. K-map is similar to truth table because it presents all of the positive value. Okay, it represents all of the positive value of input variable and the resulting output of each variable. K-map is represented by an array of cells in which each cell represents a binary value. It provides a systematic method for simplifying Boolean operation and could produce the simplest. Okay, it can produce, could produce the simplest SOP or POS expression. Okay, K-map can be used for expression with 2, 3, 4, 5 variable. Okay, so how many number of cents that you predict you're going to have? You have 2 to n. Okay, n is the number of variable. For example, if you have three variable a, b, c, then you know you're going to have 2 to the power of 3 variable here. You're going to know that you're going to have 8 cell. Okay, so for example, if you have 2 variable K-map, okay, 2 variable K-map means that you have a, b. So you have 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then for example, if you have function is 0, 1, 1, 0. Okay, so first for the K-map, you have 2 variable K-map. You have a, you have your b. Okay, and you have 4 possible number because 2, to the power of 2, so you have 4 cell. So this is correct because you have 4 cell. Now B can be either 0 or 1, and A can be either 0 or 0. So if you have A, B 0, it will result in 0. If you have A 0, B 1, you have 1. And you have A 0, if your A is 1 and your B is 0, so you have this as 1 and this is both 1. And if A and B is 1, you have this as 0. Okay, so this is way one of the way. Okay, see the camera. So you can try with the rest on the page 37. It's the same thing for verb on the slide of PDF of the page 38. Now we try to see a more advanced example. Okay, so if the question, for example, given following standard SOP form, complete truth table, and KMAP. Okay, so they give us this function. Okay, and it's mentioned is SOP form. SOP form. So this one is exactly the function that produce value of 1. Okay, so far so good. And for example, if your A, because it's if your A is actually 1 and A bar is to be your 0. Okay, so of course you have 3 input variable. Okay, then this is your input in A, B, and C. Okay, and you know this is F. Okay, dimension given SOP form, complete the table, and KMAP. So you know for this case is where the function will have 1 value. Okay, so first A bar, B bar, C. So this is actually 0, 0, 1. 0, 0, 1 we produce 1. 0, 1, 0 we produce also 1, and after that 1, 1, 0, 1, 1, 0, 0, 1, 2, 3, 4, 5, 6. Okay, and next one is 1, 1, 0, 1, 1, 0 is your 1. Next one is all 1, this one. So the rest will be 0, 0, 0, 0. Okay, 1, 2, 3, 4, 5, 6, 7, 8. And you guys know this is the standard SOP form. Now we want to complete the truth table. Okay, the truth table, because it's 3 variable, you can have A, B, C. Okay, you cannot map, and you can have what, because it's BC, right? So it have 4 possible inputs variable, and A you have only 2, means it can be either 0 or 1. And this one, however, it can be from 0, 0, 1, 1, 0, and 1, 1. Okay, and we take this into account, then we know that 0, 0, 1, 0, 0, 1, 1, 1. Okay, okay, and then another example you can try on the page 40. Okay, you guys can try from the page 40 of the PowerPoint or PDF that I share in the class. And you can also try 41. It is the same thing, it's just more variable, so the table look more confusing or whatever, it's the same. It's just the same. The concept is the same. Okay, if you guys understand, please contact me. So after this, we will go into K-map simplification. Okay. So see you guys in the next class. Thank you.